This video is going to be an extension of a pre-electrochemistry video that is already available, and we're going to build off of the statement that we previously made, that the curl of a gradient is zero, and we're going to apply that to an electrochemical cell. The curl, remember, is del cross. The gradient is just the product of del with a vector. Here the generic vector we'll call A. So in the square brackets here we've got del A, that's the gradient or a slope. The curl of the slope or the curl of the gradient is zero. For our purposes, let A be equal to potential energy. So this implies that so I'm just going to replace A with potential energy. So the curl of our potential energy equals zero. And we know from previous videos and just from first principles that the gradient of potential energy is a minus force. And so our interpretation of this statement is that the curl of this change in potential energy is zero. The change in potential energy, or the gradient of the change in potential energy, is a minus force. Therefore we conclude, seen as this equals zero, we can say that the zero net force on an electron in an electric field whose curl is zero. So remember from a previous video we said that according to electromagnetic theory, a static electric field has zero curl. That's how we were able to say that because the curl of a gradient is zero, the electric field is a gradient. The electric field with a test particle, let's say an electron in this case, provides a force. By definition, we can have a negative force if we compare this now, this change in electric field with a change in potential. So in short, we've got an issue. So our goal in electrochemistry is to make electrons move. But to make electrons move, there has to be forces. And we've just seen that right now there is no force. So I'm going to clear this board and we'll look at a diagram of the curl of the electron. Okay, so I've cleared up the board and I've plotted, first of all, before we look at what we plotted, we had this original equation. The curl of this potential energy gradient is zero. So we said that the potential energy gradient is a minus force, so there's zero force on an electron if placed in this electric field. If we actually plot potential energy against location, and we have a location between 2 points A and C, so let this point be A, let this point be C, where A just represents an anode, so A for anode, and C represents a cathode, C for cathode. Well, we can see that if I were actually to plot this again, if A and C were on the same point, so let this point equal A, which equals C. If the anode and the cathode were on the same point, then there would be, I guess, if there were no net physical separation between the anode and cathode, then there'd be absolutely no curl. So arguably that diagram is less useful. So if we compare this where clearly the anode and cathode are not on the same point in space versus where they are in the same point in space, then clearly when I look at a curl, which is a rotation, I have an area. And this area inside, so let this area here, this is proportional to the force on the electron. Here there is no area, so there is no force on the electron. So in this case, there is no area. So what this diagram tells us is that if I want to, in my electrochemical cell, force my electron to move, encourage the flow of electrons, which is the goal behind electrochemistry, then I need to separate these points, these objects, the anode and the cathode. I can't have them being connected in the same location. I have to physically separate them. So we can summarize this maybe with a statement. For the force on an electron in an electrostatic field to be greater than 0, the anode and the cathode must be separated. So for now, anode and cathode are just labels. Shortly in this video, we'll explain what we mean by anode and cathode, but for now, they're just labels A and C. Okay, so I'll clear this board and we'll continue. Okay, so now we're going to start to look at what we mean previously by anode and cathode, or the labels A and C. We're going to start by looking at a voltaic cell, which is also known as a galvanic cell. So if you were to build this in the lab, and typically you do in a general chemistry course, you might have a beaker and another beaker. So these could be two beakers. We could connect them by something called a salt bridge. A salt bridge is just an object that allows ions to transition between the beakers. It could be a piece of filter paper dipped in a salty solution. The salt bridge, to be honest, is just a connection. The nature of that connection is not of absolute importance to us. We're going to have an electrode in one of the beakers. This is typically a piece of metal. So an electrode, we're going to have a voltmeter that connects the electrodes together. And if it's a voltaic cell, then this is going to read a positive voltage. If it's a voltaic cell, it reads a positive voltage. We need some solution in these beakers. So I'm going to let this electrode be a metal, and the phase is solid, so it's a solid wire of metal, or a solid metal wire. And inside here, typically you would have the same metal, but in its cationic form. So I'm just going to write a plus charge. It might have more than one plus charge, but it's cationic, so it's positively charged. And it's aqueous because it would be soluble. So I've got a mixture of a metal in its solid form and a metal cation in its aqueous form. Likewise here, I can either have the same metal, which wouldn't be useful in this circumstance. If I want a positive voltage, rather than look at concentration effects, we'll just look at a different metal. So let's say this is metal prime, where the prime just means different than this metal here. And we would have metal prime plus aqueous. So again, the prime just associates it with this metal. It's a cation, it's aqueous. And we're going to call, well, first of all, we're going to look at the flow of electrons. Let's look at the flow of electrons. So the way I've designed this cell, and this is the way I would encourage you to learn how to draw it. We've got a clockwise flow of electrons. So we have a clockwise flow of electrons. The way I've drawn this with a clockwise flow of electrons, the electrode on the left is called the anode. The electrode on the right is called the cathode. So these were our labels A and C in the previous part of this video. And then there's an expression that will allow you to remember the difference between the anode and the cathode. So this is an ox. So I like to make a Halloween joke here for my students. If you and your significant other are going on a Halloween party and you're looking for a costume, go as an ox and a red cat. So this is something I would remember. We know that at the anode, the process oxidation occurs. So at the anode, we have oxidation. And at the cathode, we have the process of reduction. So an ox and a red cat. So if you show up to a party dressed as an ox or a red cat, any scientist in the room will get the joke. Okay, so we've labeled our galvanic cell. Let's go ahead and see what the ions are doing. So I'll try and use red here to distinguish. I have red and black, so I'll try and use my colors judiciously but not gratuitously. So at the cathode, we should point out as well that in a galvanic cell, the cathode is the positively charged electrode, and the anode is the negatively charged electrode. Okay. So this is true in a galvanic cell. So at the cathode, there's going to be the transition of metal cations towards the plate or the electrode. So these cations are going to be attracted to the cathode. Conversely, in the anode of a voltaic cell, the metal prime cations are going to be secreted from or excreted from the electrode. So look at the direction of flow. The cations go towards the plate. The cations are produced from the plate. Because of this motion of the cations towards the plate, so you could imagine the electron is coming through, it attracts the cation and the electron produce the metal. So we know that we have plating of the cathode. So the cathode is plated with M Again, you've got the incoming metal cation, the incoming electron. The charges cancel and you get the uncharged metal. So we have therefore the plating or the contribution of extra mass to the cathode. So we have a mass gain. And you could weigh your electrode before you connect it up in this cell. You could let the cell run for a period of time, stop the cell running, and then go weigh the cathode again, and its mass would increase. Conversely, if we look at the anode, we've got a loss of electrons, so the electrons are going away. So some of our metal here in the electrode has now lost its electron, and now it's become positively charged, and it now dissolves in this solution. So the anode is depleted. I think I've misspelled depleted. So we have a mass loss. And obviously conservation of mass would apply. So the mass that's lost here should equal the mass gain over here. And again, we can measure these electrodes before and after the fact, and we can see what's happening. So to give you a quick oversimplification of what's happening here, we want to incorporate the electric field. So again, I'll caution you, this is going to be an oversimplification, but not a useless oversimplification. If we consider this electrode and this electrode to be plates that have a positive and negative charge respectively, so if I consider this electrode with its positive charge, again because the cathode, versus this plate with its negative charge because it's the anode. So cathode, to make sure you can see this, cathode and anode. Then we know from electrostatic theory that the electric field would always be from the positive electrode to the negative electrode. So we'll go in that direction. And we'll assume that it's parallel electric field. Again, this is an oversimplification. But not a useless oversimplification. So over here, for example, we could look at, well, I think I've probably run out of space here. So I think we'll start again with this up here, and then we'll look at a specific example. Okay, so I've represented our diagram here. Let's adjust that a little bit. Okay, so we have the anode and the cathode of our voltaic cell. We're doing an oversimplification, useful but not an accurate representation, but we have an approximate electric field going from the cathode to the anode. We know here, this addition here is the flow of particles. So I know that we had a clockwise flow of electrons. So that would be a negative charge particle, where E is just a generic charge particle. The negative means it's a negative electron. A positive charge would go in the direction of the electric field. So therefore the electron is the opposite of a positive charge, so it would go against the electric field. And let's say that our two beakers or our two electrodes are about 25 centimeters apart, which is about realistic. You know, if you were going to make this in the lab, your beakers would be reasonably, order of magnitude about 25 centimeters apart. And let's look at some chemicals that would achieve this. So for example, to give a specific example, the anode could be a mixture of aluminum and aqueous aluminum. So remember we have the metal and its cation, so let the anode be aluminum solid and let the aqueous solution be aluminum 3 plus aqueous. And let the cathode be iron solid, so Fe solid, and its aqueous solution be Fe2 plus aqueous. Okay. So there's some equations that are going to become useful now. So we're going to calculate the voltage. So we said that because it's voltaic, it's got a positive voltage, but let's actually quantify that. So there's an equation that says that the E, or the voltage, for now, rather than tell you why, I'll just say that in most general chemistry books, capital E is the symbol used for voltage. So, and cell here just means voltaic cell. Standard means under standard conditions, so think back to thermodynamics. So 25 degrees Celsius, that type of thing. So the standard cell potential, or the standard voltage of this cell, is going to be the voltage at the cathode minus the voltage at the anode. So this is an equation that you should memorize. It's going to be very useful at the general chemistry level. And remember that we know from our little expression here, we know where oxidation and reduction are occurring. So all I need now is some values. So typically you're given values in an assessment. They're called a value of reduction potentials. So I'm going to provide them here. So we've got iron 2 plus aqueous plus 2 electrons to give iron. We're told that the reduction potential for this is negative 0.44 volts. So that would be given to you in any assessment. We also know that aluminum 3 plus aqueous plus 3 electrons to give solid aluminum. Here the standard reduction potential is negative 1.66 volts. So let's say this is the information we need. This is the equation that needs it. And now we're going to calculate E cell. So the standard cell potential of our galvanic cell here is going to be the cathode. The cathode is the iron material, so we use the iron value. So it's negative 0.44 volts. Minus, and then the anode value, the anode is the aluminum value, so we take the aluminum value, which is minus 1.66 volts. And this is going to sum to positive 1.22 volts. Crucially, we know it's positive. We knew a priori it's positive because that's what a voltaic cell is. So had this been negative, we would have done something wrong. So we knew it had to be positive. So recall that now we know what E standard cell is. And we know, as I said, it's plus 1.22 volts. We know that this is the change in the voltage. It's essentially the voltage difference between these two plates, dV. And we know that dV from a previous video is minus the electric field dotted with the distance of separation of two plates. So we've got this expression here. that you'll recall from a previous video, where this is equal to D. Okay, so let's go ahead and solve for E, the electric field strength. The electric field strength is therefore minus, because I don't want the minus E, so I bring the minus over to the dV. So that's going to be minus 1.22 volts. And then I bring the D downstairs. Well, the D is 25 centimeters. I need this in units of meter. So to get from centimeter to meter, I just divide by 100. So it's 0.25 meter. And this is equal to negative 4.88 volts per meter. Volts per meter are also known as Newton per Coulomb. And we know that Newton is the unit of force and Coulomb is the unit of charge. So I've got force per unit charge. So the electric field allows the production of a force. And remember, it's the force that we've generated that's non-zero. The force is now going to force the electric flow through our cell. Okay. So before we finish with this board, let's remind each other of the following and we'll interpret what's going on. So we've said previously that a negative change in potential energy is proportional to a positive charge moving in the direction of the electric field. Okay. Now, a negative change in potential energy, imagine that's like falling downhill. So you don't, for example, if you consider water, if you spill water, it's naturally going to go down. It's naturally going to lose potential energy. It's going to fall down. So let's say that's the thing that happens naturally. We don't have to force that to happen. A voltaic cell naturally, through the laws of nature, produces a voltage. So let's say we don't have to force that to happen. It generates its own natural force. So we would assume that this cell was operating it's operating by following the direction of a change of negative potential energy. So if we assume a priori that there's a negative, or the change in potential energy is negative here, then this must mean a positive charge is moving in the direction of the electric field. Yes, a positive charge moving exactly in the direction of the electric field. Well, that reinterpreted for electrons would be electrons, which are negatively charged, moving against the electric field. And as we said, that would be a clockwise motion of electrons. So everything ties in with what we've said. We've got a non-zero force, and the negative sign we can interpret just because our charge is negative, because we have an electron. So we have a positive force forcing our negative electrons around the circuit. So in concluding this diagram, let's stop and look at the chemical reaction that's happening in this diagram, and then we'll actually write a cell diagram that's a useful abbreviation of these more long-winded diagrams. So I know I've got oxidation at the anode and reduction at the cathode from my abbreviation up here. So let's look what I have. So oxidation means I have electrons as products. So I've got oxidation with aluminum, so that means I have aluminum solid giving me aluminum 3 plus aqueous and 3 electrons. So this is oxidation. Again, oxidation because I have electrons as a product. I also have reduction at the cathode, that's my ion chemistry. So here I have electrons as reactants, so ion 2 plus aqueous plus 2 electrons to give ion solid. So this is reduction. We know from our balancing redox equations in acid and base medium that the electrons are not separate electrons in these half equations. The electrons are the same. So to make 2 and 3 the same, I've got to scale the aluminum half equation by 2. The 2 is now going to hit the 3 and make it 6 electrons. And I've got to scale this half equation by 3. The 3 is going to hit that 2 electron and make it 6 electrons. So by scaling these half equations by 2 and 3 respectively, I've ensured I have one identical number of electrons overall. If I now add these equations together to write one overall equation, I get the following. 2 aluminum and 3 iron, 2 cations. I don't need to worry about my 6 electrons because they're going to cancel the 6 electrons up here, so my electrons always cancel. The 2 is going to hit the aluminum though, so I get 2 aluminum 3 plus aqueous, and then finally 3 iron. So this is my overall chemical reaction. My cell diagram, however, I'm just going to look at the diagram left to right. On the left, I have aluminum solid, single parallel line. Then I have aluminum 3 plus aqueous, double parallel line. So in the cell diagram notation, the single parallel line represents a phase change from the solid to the aqueous phase. The double parallel line represents the salt bridge, which essentially is the connection between both beakers. And then at the cathode side, I have this mixture here. So I have iron 2 plus aqueous, single parallel line because I have a phase change from aqueous to solid, and then iron solid. So this is my cell diagram. Notice I can see from my cell diagram, it's important that a skill that a student has is to be able to go from a cell diagram to a chemical reaction and vice versa. You might be given one of them and you might need the other one to do a specific calculation. But we can see that if we just read it left to right, we've got aluminum going to aluminum 3 plus. Well, that's just oxidation. At the anode, the cathode. No, sorry, the anode, an ox. At the anode. And then reading this again, left to right, we've got the cation going to give the neutral element. Well, that's just reduction. And we know reduction happens at the cathode. Okay, so this will conclude this part of the video on galvanic cells or voltaic cells. Clean up the board, we'll look at electrolytic cells. So we continue now to move away from voltaic cells. We're now going to look at electrolytic cells. Electrolytic cells would actually have a negative voltage, that's how you know them. So if we want to actually apply a positive force, a useful force, if we want to establish a useful force to do something, we actually have to install a battery onto this. So I'm going to start with our beakers. If we were going to make this in the lab, we'd probably use beakers. So we've got two beakers. Let's go ahead and put our electrodes inside. Just like we did earlier with the other type of cell. So let's say that this is, let's say this electrode is M prime solid. This electrode is just M solid. The prime just means that it's different than the unprimed. We have to go ahead and install a battery now. So we'll represent the battery as two parallel lines, a long one and a short one, where the longer of the two lines is the positively charged terminal. The shorter of the two is the negatively charged terminal. And obviously electrons are repelled from negative charges, so we're going to have a flow of electrons counterclockwise the way I've drawn this. Electrons are attracted to the positive, electrons are repelled by the negative. If you were somebody that looked at the flow of positive charge, the positive charge would be clockwise. But in chemistry, we consider the flow of electrons. So this is going to be in a solution. And we have M prime positive aqueous. So the cation of the electrode. And here we just have M positive aqueous. Again, the cation of the electrode. And on this occasion, I actually have the cathode on my left, and I have the anode on my right, the way I've drawn this. On this occasion, the cathode is negatively charged with respect to a positive anode. So notice that this is different than the previous case, and that's because the electrolytic cell essentially is the opposite of the galvanic cell, where here the electrolytic cell requires a voltage to be given to it, whereas the galvanic cell produces a voltage. However, our expression still applies. So the cathode is still the site of reduction, and the anode is still the site of oxidation. Okay, we need to connect these beakers by a bridge. So the electron is going to flow that way. So now the electron is flowing counterclockwise. So we're going to annotate this a little bit with, if we look at the cathode, for example. So on the cathode, we can have migration of the cations towards the cathode. So we'd have M prime plus aqueous moving towards the plate. So we can say that at the cathode is plated. So recall from the galvanic cell, the cathode was also plated. The cathode is always plated. So there's a mass gain. If we look at the anode, then the anode is going to lose M plus aqueous. It's going to lose mass in the form of M plus aqueous. So the anode is depleted. And this is a mass loss. So you could weigh these electrodes ahead of time. You could follow conservation of mass to make sure that you haven't created or destroyed mass. And this makes sense. We've got electrons being pulled out of the electrode here, the anode. Electrons are being removed, and so the metal, now being deprived of its electron, just dissolves into the medium as the cation. And here we're essentially have a surplus of electrons, which now attracts the cation, which plates the cathode and increases its mass. So this is exactly the same setup as we had with the galvanic cell. Again, I'm going to do an oversimplification, so I'll acknowledge that this is an oversimplification here. But if we just look at the electrodes themselves, the anode and the cathode, so we've got the cathode, which in this occasion is negative, the anode, which in this occasion is positive. Then we know from electrostatics that the electric field will flow from the positive to the negative. So everything's the same, but the flow of the electrons is in the opposite direction. Okay, so we'll clear the board and we'll continue this inspection on a fresh board. Okay, so we've cleaned up the board a bit. We've represented our last expression where we've oversimplified and we have just a static electric field between two plates, or at least that's the oversimplified analogy. We have the negative cathode, the positive anode, so the field is going from positive to negative. Let's give some specific examples. Let's say that the cathode in this case is a mixture of nickel solid with dissolved nickel cations. And let's say that the anode in this case is a mixture of copper solid as the electrode and copper 2+ anions as the medium. Let's again say that these are separated, the beakers or what have you, are separated by 25 centimeters, which would be a realistic separation. We've again got our equation. E standard cell is E standard cathode minus E standard anode. And we're given reduction potentials, standard reduction potentials, which in this case are nickel 2+ aqueous plus 2 electrons to give nickel solid. Here the standard reduction potential is negative 0.25 volts. For copper, we have copper 2+ aqueous, 2 electrons to give copper, and here the standard reduction potential is positive 0.34 volts. Okay, so on this occasion we know that E standard cell, or the voltage in this, which we know a priori must be negative because it's an electrolytic cell, is going to be the cathode value, which is the nickel value, which is negative 0.25 volts, minus the anode value, which in this case is the copper value, which is plus 0.34 volts, which here, if we sum that together, it's negative 0.59 volts. So again, we knew it had to be negative, and that's exactly why it's an electrolytic cell. So we know that E standard cell is negative 0.59 volts. And we know that this is the change in voltage, dV. And we know that the change in voltage is minus the electric field dotted with the separation of the two plates, or electrodes in this case, D. So we're going to solve for the electric field, see what type of electric field we've generated here that's causing these electrons to flow. So the electric field here is going to be, if we take the negative sign over here, so we're going to take that negative sign over to the other side, so it's going to be a positive voltage, so plus 0.59 volts, divided by 25 centimeters in meter, so we divide it by 100, so 0.25 meter, and that's equal to a positive value, 2.36 volts per meter, which is also, in terms of dimensional analysis, equal to Newton per Coulomb. Newton is the unit of force, so we have a force here. Okay, so let's have a look what's happening. So we'll write something from a previous video again, something that we alluded to earlier. So we know that a negative change in potential energy is proportional to a positive charge that's moving in the direction of the electric field. So this is something that would occur naturally. Now we know by definition with an electrolytic cell, because it naturally has a negative voltage, if we wanted something to naturally happen, we'd have to overcome that negative voltage. It's like we start in a hole. We've got to add some voltage to get out of that hole. So this is what would naturally happen. There'd be a natural change in potential energy that would be a decrease in potential energy. Well, that happens when a positive charge is moving in the direction of the electric field. But what we have in an electrolytic cell, if you recall from the previous slide, the electric flow was moving, or the electrons were moving counterclockwise. So this negative charge moving that way, the electrons were moving counterclockwise. So therefore, positive charge would be moving clockwise. So it's the opposite flow of electrons, the way I drew it in the previous board to this one. So that means that RL, instead of a positive charge moving in the direction of the electric field, what's actually happening with an electrolytic cell is I've got a negative charge moving in the direction of the electric field, which in this diagram are both right to left. So here, in an electrolytic cell, we actually have a positive change in potential energy, since a negative charge is moving in the direction of the electric field. Now, because of this, it doesn't and I'll use quote, naturally happen. So it must be forced. It doesn't naturally happen, it must be forced. And so you can think of an electrolytic cell as an appliance, where an appliance like a TV has the ability to conduct electrons, electric flow, but you have to force it by connecting it to a main supply or a battery supply. Conversely, a voltaic cell naturally causes electrons to flow. So you've essentially got batteries and appliances. Galvanic voltaic cells are batteries. Electrolytic cells are appliances that require batteries. And I would take some time to reconcile this idea of positive or negative change in potential energy as you consider this content. Last thing we need to do is clear the board, and we'll just summarize the chemical reactions in the cell diagram. Okay, so the chemical reaction going on in this particular cell, we had copper was being oxidized because copper is at the anode, and the anode is the site of oxidation. So we have copper solid becoming copper 2+ aqueous and 2 electrons. And then at the cathode we had the nickel chemistry, so that was the site of reduction. So we have nickel 2+ aqueous and 2 electrons to give nickel solid. So we've got oxidation and reduction respectively. If we combine those two together, here we don't need to scale as we did earlier because we have the same number of electrons. So we could just write copper solid plus nickel 2+ aqueous to give copper 2+ aqueous and nickel solid. Again, it's important that a student can go back and forth between the chemical reaction and the cell diagram. If we read this thing left to right, we can see that we have nickel as our electrode, specifically our cathode, but there's a phase boundary between the solid and the aqueous phase. So we've got nickel 2+ aqueous. Then we've got our connection between electrodes, our salt bridge. Then we've got copper 2+ aqueous, phase boundary between the aqueous phase and the solid phase, and then a solid copper anode. So this would be our cell diagram, and this will conclude this introductory lecture on electrochem for a general chemistry audience.